right, let's get started. Welcome everyone to our second robotics colloquium of the quarter. It's a pleasure to have Kiana. Kiana's been at UW far longer than me, so she doesn't need an introduction. But Kiana and I met a couple months ago at this VC dinner, and she said a lot of really interesting things. And so I want her to share a lot of those insights with you. And she's one of the leading figures in robot learning, sim to real, VLMs, all really interesting things. And so I'm excited to hear her talk. Please take it away.
Thank you for the introduction. See, that was better than what I wrote, the formal one. Hi, everyone. I've been here since 2015. I was a PhD student at UW, started with theoretical computer science, actually, surprisingly. And then realized that I want to do something more applied, so computer vision, and then I think I can identify as a roboticist now. So today I'm going to talk about a couple of our findings, my team and I at AI2. Take it as suggestion, but I think it might be a little bit different from how you all think about problems. So I just thought I can share some of our findings with you. And let's start controversial. The CEO of this company, this startup called Figure, tweeted a couple of months ago that ChatGPT moment of robotics is here. Then he posted this video of the robot, basically the humanoid robot. Oh, this is such a bad quality here. Great. But yeah, it's basically like opening the coffee maker and pushing a button to making a coffee, not even picking up the mug. People got mad. People were like, oh, we've been doing this for 2 years. Like, this is from UT Austin. Why are you calling this the ChatGPT moment of robotics? And that made me think, well, obviously, like, a lot of that was hyped up, and I don't think he actually believed in that. But the question is, why ChatGPT of robotics is not here? And I want to basically like build upon a lot of metaphors and like the correlation between robotics and language today to see why we are where we are today and how we can move past that. So I think answering that question requires some preliminary questions to be answered. What is the definition of ChatGPT of robotics? What is it? What is your guys' definition of ChatGPT of robotics?
User-friendly?
User-friendly?
Maybe like grounded in natural language understanding?
Grounded in natural language?
It's a task generalist. You can do a lot of tasks.
Do a lot of tasks. So maybe let's answer what makes ChatGPT ChatGPT. Why is everybody so excited about ChatGPT? Large range of tasks. It can do a variety of different tasks. It's not limited to just part of speech recognition or next word prediction. It generalizes to truly unseen scenarios. A lot of the scenarios has never been in domain. It's not templated. It's like truly natural. It's easy to adapt to new domains. So people do in context learning, or they do all these sort of like tricks that, or even do RLHF to make it be better at having conversations. And finally, it works with any language. It works with English, it works with French, and Python is a language. I call that a language, and I think that's actually one of the benefits of it. Okay, so let's talk about what would each of these mean in robotics. Large range of tasks, again, same concept. We want the policy that we have, we want it to do a large range of tasks. We want the ChatGPT of robotics to be able to generalize to truly unseen scenarios. We want it to be easy to adapt to new domains. And I translate any language to any embodiment. OK. So what made this moment? What made the language models to be so successful? There's a data, internet scale, large scale, a variety of different topics. They do a pre-training. They get a foundation model from that. They do fine-tuning or adaptation, and they get ChatGPT. So today I'm going to just talk about how I and my team have been thinking about all of these different parts of these components of this pipeline. And maybe you all can join forces to put this pipeline together and have that real ChatGPT moment of robotics. OK, let's talk about data. Where can we get data? We can get the data from real world. We can get the data for some specific tasks that we are interested in. For example, let's say if you want to just open a cabinet, let's just get a lot of data for that specific task. But that's limited. That's small scale. That's just for that specific task. Let's join forces, the whole community. We just put together these all of the data that we have, different embodiments, different tasks. Let's see what we can get out of it. It works to some extent. It is still not as scalable as we want it to be for a variety of reasons. And then simulation, it has privileged knowledge, and we can just run planners to get a lot of data. Obviously, the sim-to-real gap is a problem. So first, I want to talk to you about how we've been thinking about getting data from simulation and some of the interesting findings that we've had. For those of you who've been here last year, our team lead gave a talk on this. I'm going to go through it as quickly as I can, just for the sake of completeness. So basically, old story, the numbers were not great. We were frustrated with them. And the architectures were just getting more and more complex. We just wanted a simple solution that is not modular, that is not having like a lot of components. We just wanted to see how far can we push this simplicity for a very simple like end-to-end model. What if we trained the models on shortest path trajectories? Would it explore when deployed in real world or in simulation? And actually, can we get this slide off by any chance? I think that would make the videos perfect. Thank you so much. OK, so let's look at this one again. So basically, we use the privileged knowledge from the simulation. We get some shortest path trajectory. We train on it. The question is, can this model explore? And the answer is yes, it could. It was able to, it showed a lot of capabilities that we did not expect it to have. If anything, there were actually a couple of papers that came out before we started working on this project that were showing that if you train on shortest path, you will not get good results. So what was different? We had diverse simulation data. So we bumped up the number of scenes, the number of trajectories we are obtaining. And we used a transformer architecture, which basically used a pre-trained frozen image and text encoders to basically encode the visual observations and the task, and get a token that we can use for each time step to decode and just predict the actions. So given an RGB observation and a task, let's predict actions. And we did extreme data augmentation. This is the extreme that we pushed this. And these are all that made the sim-to-real transfer very easy. So all the tricks that I'm mentioning here are the tricks that has made the very small sim-to-real gap available in the rest of the projects that I'm going to talk about today. OK, so what are the tasks that we are considering? We had a variety of different tasks for this specific project. We limited it to a navigation, object navigation, given a description of an object that can be whether it's like what room this object is on, what category this object is, what is an instance description of it, navigate to the object, pick up an object, or fetch it, which is explore an environment until you find it and then pick it up. And we also had the task of room visit. So what were we able to do? So we generated a bunch of data, shortest path trajectories, and we saw that training just supervised to predict the actions. we saw that this model learns to infer spatial relationships. So for example, for the task of navigate to the highest fruit in the kitchen, it learns how to go explore the environment to see all the fruits that are available and then infer which one is the highest and issue a done action by the target object. The other one was we saw that we can perform task-specific behaviors, such as like looking for a computer on a sofa, so looking for only on surfaces that are valid, which is on the sofas for this target object. And because of all the data augmentation that we had, and plus the backbone, the frozen backbone that we had, we were able to just directly transfer to the real world.
This particular technique of solving many determinized problems is known in the community as sort of determinization via hindsight. And like you had mentioned, there's a submodularity gap between solving the POMDP and solving the sort of determinized MDP. And oftentimes that gap is because the determinized problem doesn't have any information gathering actions, right? Because you've already determinized the world. So if you want to pick up a coffee mug and you don't know where it is, in the determinized world, the coffee mug is in front of you, and so you pick that up. And so you pick up another coffee mug that's in front of you. But in the non-determinized world, the action that you need to take is to flip on the lights, which you will never do because you've already determinized the world. So as I was looking at this and wondering about the efficiency, or at least the seemingly small gap between, the submodularity gap between the determinized problem and the POMDP, I was wondering whether that might be a feature of the problem that you're solving, that there are no truly information-seeking actions that are needed, like no light needs to be turned on in this room for you to be able to see something. As a consequence, the determinized problem is actually a pretty good proxy for the POMDP.
That's a good point, actually. I think I've given the talk about this project a couple of times. I've never came upon that observation. I think that's actually true, that this is the benefit of having that determinism. Okay. So let me ask you, do you think ChatGPT of Moment of Robotics is here? We are doing some like larger range of tasks, but not fully. We can generalize to truly unseen environments because really this is like we are only training in simulation and transferring to real, so it's truly unseen. But the other ones are still not solved. So no, I don't think ChatGPT Moment of Robotics is still here. Why though? What are the problems? Let's dig deeper and see what are the places that we need to improve. So if you look at the performance of our model, especially if you're not using the detection, the off-the-shelf detection, RGB only, the performance is not good. We are not happy about this. And that's like basically because we are doing imitation learning. Imitation learning, fast and efficient in training, deep, high-capacity models, but it comes with a cons. There is an insufficient state space exploration. On the other hand, RL, it's learning through trial and error. It's not limited to predefined skills, but it's slow and unstable training. And generally, a lot of the architectures that are out there, because of the speed, they're very shallow architectures. Yep.
So your imitation learning is on experts that you're getting from a computational oracle, right?
Yeah.
So you can just like randomize the state and get like coverage for free, right?
Yeah.
So you don't actually, like, why would you need RL in that setting? Like, shouldn't you just be able to do more computational oracle generation over imitation learning?
So we tried that. So let me make sure that I understand that correctly. So you are saying that at each step, like roll out the policy to get to the state that is not observed by the original expert, and then take on from there and roll out the expert again.
Like you never need RL if you have like or you might not need RL if you have an oracle, right?
So we examined that. That's actually very valid point. We examined with it, and the results were still suboptimal because those suboptimal behaviors that the model will learn, the data that we would collect from that, it would just amplify it. So we were not happy about that. And also, spoiler alert, we found a way that it works really well. So we ended up just going that way. But I'll explain. But that was actually like one of the things that we wanted to study more rigorously. But I'll explain why we didn't. Okay, so if I had a nickel for every time that I talked about the Spark paper and somebody said, why not just fine tune with RL, I would have been a billionaire. So yeah, let's just fine tune it. There's just 3 tiny little problems. It takes 2,560 GPU hour days. The training is unstable, and if you just like directly start fine tuning, you'll performance drops, and you're basically starting from scratch. And it requires handcrafted reward for each of the tasks that I described. So because of these tiny problems, there were a couple of steps that we need to take. Okay, first of all, this 2,560 GPU days, it's not really, even like at an academic institute like AI2, that's not possible. So first, let's see how we can enable large-scale RL training. And that's where Polyformer comes into place. This is the work that is going to be presented in a few weeks in Coral. We just wanted to enable fast RL with transformers. We just chose the task of navigation first because we just wanted to simplify the problem first. Okay, so we do 100 of parallel rollouts in diverse environments. We use an architecture transformer-based policy, very similar to Spark, and we do extensive caching. We do a KV caching, which is not new to the AI community. LLMs have been, like in that region, they have been using it a lot, but we just brought it to the robotics policies. So here's how the architecture look like. We basically have the RGB observation and the goal specification, both using some frozen visual encoder and text encoder, and then optionally we can have a bounding box. Basically, we realized that if we want to leverage some of these like large foundation models, like using the bounding box to be able to capture the data of the objects that we have never seen in the simulation, we do want to have a way of injecting that information from the VLMs. So that's why we basically like have this optional bounding box we have a variation of our policy that we can have a bounding box. Okay, great. So the rest is pretty similar to the Spark, and we basically do the KV caching on our causal transformer decoder. Now, one might argue that why are you doing the caching in that region? You can do that on any of the other stages, and we showed that that's actually the one that brings us the most improvement on the FPS. Okay, we saw that we just get continual improvement with scale. The longer the number of training steps, the better numbers we can get on our benchmark. And because we wanted to make sure that this is not just specific to one embodiment, we tested this out on 2 separate embodiments, but basically we were training a model for each of them, so it's not one model policy for all, but we saw that we can do the sim-to-real transfer really well as well. Okay, and these are a couple of like downstream applications that because we were having that bounding box as an input to the policy, so we could use any off-the-shelf model that we want to get a bounding box of the target object that we want. So now we can follow an object. Now we can do multi-object navigation because we are basically like adding a modular component to this, that the semantic reasoning and semantic object recognition is being passed on to another model. Okay, great. So we show robust performance, and it works great. We see a really big improvement compared to the imitation learning model. So going from 55 to 85. That's great progress, right? Except when we go to tasks that have longer horizon planning or have like the action space is larger, this method does not work. So for example, for the task of fetch, where the action space is much bigger, it includes all the actions on the arm as well, it really fails to get off the ground. So why not bringing the best of both worlds together and combine them? Okay, so this is the next project, and that thing you see up there is because I was presenting Spock at CVPR this year. It was early summer, and 2 people came separately. They came to our poster session, and they were like, have you tried fine-tuning with RL? And I said, yes, it was actually in the beginning of this project. We still didn't have results, and I said, yes, and we'll hopefully have good results by the end of summer. And one of them looked into my face and said, oh, I wouldn't count on it. A lot of people have tried. I don't think you can make it work this fast. Which is, okay, first of all, don't say that. But also, I'm glad to say that. I think we have really good results by then. Okay. So just to recap, we had the pre-training, the results weren't good. Now we want to fine-tune that pre-trained model, and we found the recipe of how to make RL faster. So we want to put them together, fine-tune this model to get good results, and basically improve on that. It's not really super complicated. I don't have anything that you guys don't know. It's just a couple of small tricks that made this work. And I don't want to oversell it. It was a learning rate that is much smaller than we usually do. It's just making the learning rate be much smaller. Disable entropy bonus, because you're starting from a model that has this sense of like what are the actions, and it doesn't need to explore as much. And separating the actor and critic, because the model has been trained for with the imitation learning gradients. And we realized that if we try to force the actor and critic to share the same backbone, it makes the training very unstable. That's it. This enabled us to do fine-tuning from an IL agent using only sparse reward. So no reward shaping. We only have whether the task was successful or not. And it's a very sparse reward, once per episode, and that's all we get. And this is the average of the results. So not only we can train our models much faster, we get to a much better performance than any other method that we evaluated on. So it's more robust compared to the baseline. All of the baselines would have like the jumpstart RL and the Perl nav. They all have a drop before they get back up again. And also every one of the small tricks that I mentioned, they're very critical. We turn each of those off, the training becomes unstable and crashes again.
I have a question about the entropy bonus.
Mm-hmm.
So like, did you guys do an ablation of like all the other tricks with and without the entropy bonus? Like, I guess my question is because in the past, okay.
Yeah. So each of these is we keep everything else, and we just turn off one of those tricks that I'm showing.
And so like, I guess like empirically, like with the entropy bonus, was it that like the RL was unlearning the stuff that I learned in imitation learning?
Yeah, exactly.
Okay.
So I don't think that that's the only way, like disabling it is the only way. Probably there are some tricks that you can do to like reduce it in the beginning and then bringing it back up, but that's the trick that helped us do that. Okay. So the object nav, it's like one of the tasks that we have seen during the imitation learning phase, but there are also 3 other tasks. And this is the most surprising result to me. We are starting from 20% success rate on this task. With a sparse reward, and only 50 million frames of training, we get to 70% success rate. This is a very interesting finding, in my opinion, because it says that you don't have to have a perfect policy. Your imitation learning, your foundation model doesn't need to be perfect. We can still manage to get to a really, it's a really good starting point regardless.
Question.
Yeah.
So you talked about exploration in the first thing, and how you can get it, like essentially what you're getting looks something like posterior sampling. You like have different things you'll try which are temporally coherent. In the process of like RL fine-tuning, do you retain exploration, or does it like lose the ability to explore?
No, it retains.
And when you're doing the fine-tuning, like often what's hard in RL fine-tuning is like it only like makes these tiny local changes because you're doing this like IID noise at every step. Is that what's happening, or when you look at the exploration, is it like doing temporally coherent exploration during the RL fine-tuning process?
No, it is doing temporally consistent. It's like, I don't think if we were doing just a small diff with the IL policy, we would go from 20% to 70%.
In certain problems, like I guess it's just like you're missing by a little bit. Maybe it depends on your success metric, but I guess here it's like finding things in rooms, so maybe it's...
So one of them, so the object nav is exploring the environment until it sees the object, and it needs to issue a done action when it's 1 meter to the object, and the object is visible in the camera. Fetch is same, but it needs to also pick up the object. So bring the arm to the object and pick it up. And then pickup is, we initialize the agent close to the object, so you can think of it as like a tabletop pickup. And then room visit is, it needs to explore the environment, go to every room, and issue a sub-done action saying like, I'm in a new room, and then issuing done when it has visited all the rooms. Okay, so what if I want to have a new task? Let's say I have these unseen capabilities. Can I just use RL fine-tuning without having any expert trajectories in those domains? The answer is yes. So I want you to note that these tasks are not something like extremely different. So it's not like I'm starting from navigation and then generalizing to pickup. No, this is, so for example, the task of object nav rel attribute is go to the highest fruit in the kitchen. So it still needs to learn what does it mean to explore and make sure I've seen all the fruits in this room, and what does the highest mean, but it's still like the same concepts of navigation. So a lot of the skills transfer. So that's why we are able to get a reasonable success rate. And I just want to point out that these models has access to expert trajectories in that domain. So it was very interesting to see we can even achieve better than that. And this is one of the examples. So basically, let's say the realm of tasks that you're training on is like find an alarm clock and grab that alarm clock. And then the things that we are fine-tuning on are locate the lowest container in the bathroom. Can I adapt to a new embodiment? Can I get this model that I've trained on Stretch robot and fine-tune it on Locobot, which is a robot that is like Stretch is this big, Locobot is this big. Stretch has 2 cameras, Locobot has 1 camera. Action spaces are different. The rotation, center of rotation is different. Yeah, so these are the results that we basically compared success rate and SEL, which is an efficiency metric of how efficient the path was for our model and for the RL model that is trained with that specific environment, that specific embodiment. Okay. Another nice outcome is also you can get new behaviors out of it. Let's say you want to emphasize to the agent that I don't want to have any collision. So emphasize on that term. You can just add a reward function to that sparse reward, a reward term, and you can see that the agent changes its behavior. So these are the nice adaptation capabilities that comes with it. And again, we did the extensive study on seeing how well it does on our benchmarks, and it was matching the simulation results and outperforming all of the previous models. Okay, it's ChatGPT moment of robotics here.
Just a clarifying question about success. I guess like you talk about success rate, but like, is there some notion of like how long it takes to succeed? Like, and what is your perspective on that?
So-
I didn't. Did you already show that? I'm sorry.
Yeah, so that's SEL, which is so we can get the shortest path for each of the tasks that we have in simulation. So we know the shortest path, and we penalize the success by how much longer than the shortest path it took us to perform it. In terms of it's not in terms of like how long does the policy take to perform this task. It's more how much longer than the shortest path I took
When you succeeded.
when I succeeded.
When you succeeded, how much? But this is less than 1 though, so I'm just trying to understand that. Like, is it?
So
when-
it's like
when it comes to-
basically SEL it will always be smaller or equal to success rate, because I'm penalizing each of the success episodes by how much inefficient I was. So it's basically the term is I will have the shortest path length in divided by the time that it took me to complete the task.
I see.
So if it takes me exactly similar to shortest path, I will get similar success rate as similar SEL as my success rate.
I see. So I guess my interpretation of the second column, then second pair, is that you take about twice as long to succeed because it's about half as long.
Yes.
The bars are
Yeah.
2x and 1x.
Yeah, yeah.
I know it's not like, I know distributionally it's probably
Yeah,
different.
Okay. So easy adaptation to new domain.
Maybe one more clarification. Like, is there a baseline against like something that is like drop dead simple? I'm trying to understand and appreciate this, like random exploration, or like deep exploration, like pick a point, go there, go along that for a while. Like I guess I'm trying to understand, like maybe this is a follow-up to Abhishek's question of like where's the nuance here that we're seeing in terms of exploration? Or maybe you can even tell us like qualitatively when you look at it, like what's it doing that's like super clever? The quantitative results would be nice too.
Yeah, so I think qualitatively, I actually have an answer for that. When we saw how well it's exploring, so we have the top-down view in simulation at least, we can get the top-down view that it's actually going to every room and it's not going around in circles. And we saw those results and we realized, oh, this is very impressive. How can I show this to others? So we put every single one of our test trajectories. We have the top-down view. We put it all on our website so that you can go and see it, so that you know it's not, when I say it's exploring really well, I'm not just saying that, and the results are out there. Quantitatively, we actually tried to measure, I'm trying to remember, we had, in the paper, so I don't have it here, but in the paper, we have this measure that is like the number of rooms visited.
Yeah, I mean, I guess like that makes a lot of sense. I'm just wondering about baselines because it's hard to understand the nuance of what's going on. And obviously, like in certain scenarios, it's much more nuanced than others, right? Like, and so being able to see that would be useful. Or like how it would do if you run like sparse slam or some like download the average slam and then some exploration code that's available on the internet. But this is impressive still.
Yeah,
and
no,
the
I
SEL
agree.
is appreciative.
I agree. It's like sometimes it actually goes back to the conversation we just had, that we really wanted to have a baseline that is like the best, like modular or like the traditional robotics baseline for exploration. we couldn't really find that what is the best and what is the easiest that doesn't require a lot of work, like another research project worth of work to make it work, so that we can put it down there as well. But I agree with you. I'm actually very curious to see how well those models perform compared to ours as well. Okay, so we can adapt to new domains that, with an asterisk, still has to have those same skills. So I can't do go from that to solving Rubik's Cube with the hand, obviously. And do we have any embodiment? A little bit. It's still only previously seen embodiment. So I can adapt to a new embodiment, but I still need to fine tune on it. So this is not perfect. Why? What if I have a new robot? I am getting more excited about Unitree, like dog robots. Do I have to fine-tune my model? Do I have to be limited to the embodiments that I've seen in pre-training or fine-tuning? Do I have to make a robot mesh in simulation every time I'm coming up with a new robot? This doesn't seem ideal. Okay, so where does this sit in this pipeline that I talked about? This is that language component. So it's actually all of it. So the language the embodiment that I'm training on, that I'm considering, can I randomize on that? Can I do something that I can cover all of the possible languages out there? Can I train on some languages and expect it to go to totally unseen languages, unseen alphabets? Probably not. But what if I was randomizing as much that I could go to anything in between, I could interpolate?
So, quick thought here. At least for the navigation part, I wonder if hierarchy gets you there in the sense egocentric view, low-level waypoint controller, and then like lots of things are very similar, right? In the sense like you use feedback as your abstraction that lets you use many different embodiments at the low level. Like, does that work?
That's a good question. So let me first give this is great because this is an ongoing project. And I'm showing you results, but it's a project that is still like half-baked. We still don't have the baselines. We are more on the end-to-end paradigm of thinking. So that's why, and like we have access to the simulation. And we found a recipe that is working to an extent. But I 100% agree with you that we should evaluate on those baselines. Okay, this name is subject to change. As I said, this is a half-baked project, and we never have a good name until the last minute. I hate this name. We're going to change it, so don't get attached to it. But this is the goal. We want to have one policy fits all. And these are some of the robots that I just like searched the internet and like put it there. I'm sure there are plenty others that we don't, that I haven't put here. We have the simulation. We can do anything we want in simulation. What if I could just like have a block and change the shape of the block, put different cameras on it, different parts, and like have different center of rotation, and generate a bunch of data and train a model on it. So this is, let's embrace the randomness. Some of the robots will have 1 camera. Some of them will have 4 cameras. Aspect ratio, like maybe people want to put different cameras on their robots. I don't want to be limited to one specific camera setup or agent setup. What does the policy need to know about the agent? The policy needs to know the camera parameters, which is relative position, rotation, field of views, number of cameras, image width and height. But we also need to know agent parameters. What is the body's approximate collider size? What is the collider size? What is the center of rotation? For example, for Locobots, the center of rotation is the center of the agent, but for Stretch is in the front of the agent. And it actually makes a big, big difference. For those of you who have worked with Stretch, you know that if you don't pay attention to that, and you train a model in simulation, it comes and bites you later. So these are the details that you need to think about. And then optionally, you can have the robot mesh or not. It's not necessary. Okay, so we train a model on this data, and this has never seen the Stretch body. It has only seen these boxes. It has never seen the Locobot. It has never seen the Unitree agent. And for those of you who have worked with Unitree is like this big. Locobot is here. Stretch is here. Stretch has, our Stretch, the Spock version, has 2 cameras. The original Stretch has 1 camera, and it's like horizontal instead of vertical, or vertical instead of. Anyway, it's like the cameras are rotated, have different field of views. But you can see that the results are pretty consistent. So it doesn't matter, like it doesn't get affected as much by what the body looks like. So yeah, this is the body that it's trained on, different variations of that, and it can perform much better. Okay.
Sorry, I might have missed this, but like, what's the action space?
You have not missed it. Somebody forgot to put it there. So we have a discrete action space, and the action space is moving the base or moving the base forward or backward. That's 2 action, 20 centimeters. Rotating it by 30 degrees right or left. We have the arm action, which is moving the arm base of the arm and then moving the arm out, and then the gripper. And opening the gripper, and there was one more. Oh, and then issuing the done action. Done and sub-done.
And what's the task that's being evaluated?
These are all navigation only, so object nav. Cool. Let's ChatGPT moment of robotics here. So now we can do any embodiment. Great. That's great, but it's not here yet. Why? Consider a task like this. Move the water glasses from Matt's desk. Matt is one of our colleagues who always has a lot of cups on his desk. So move the water glasses from Matt's desk to the kitchen table. Just this part of it requires the agent to go explore, find the desk that belongs to Matt, which has his title right by its side, then put the biggest of those cups in the kitchen counter next to the sink, and if the tape is on Matt's desk, do this. It's not possible to capture all of these concepts in simulation. What can we do?
Why not?
Why not?
Yeah, why can't we capture them in simulation? Your simulation is better.
If you have to have like a lot of objects. There will still be a lot of objects that are not there. You will have the concept of like putting name tags on tables, on desks. We have to like generate all of this.
Or is it the
Oh, semantics, just the semantics. Just understanding the semantics, I'm arguing that we can't put all of the semantics in simulation. So I've been lying to you. I tricked you all into thinking that that's the whole pipeline. But if you think about it, I showed you in one slide that I'm using pre-trained frozen image encoder and text encoder. That's pre-training. I actually rely a lot on these for having small sim-to-real gap, for being able to train models that quickly can recognize objects. So this is where we are. This is where we need to inject those information. And that's where MolMo comes into place. So we started talking about, we were collecting data and training a model, multimodal model, for a VLM. And we were thinking, how can we make these models, these VLMs, to be robotics aware? A lot of us have worked with these large foundation models into, here and there, some components of it in our methods, but none of them are designed for robotics. We are not the first one to think of this, obviously. Our very own Dieter has worked on, and Abhishek, and I'm not sure actually who all were on that. I should not have mentioned names, but anyway, so we have RoboPoint, we have OpenVLA. These are, the community is coming to this conclusion that we need to have VLMs that are robotics aware. So how should we integrate VLMs into the system? I'm going to propose one method. There are a lot of different methods. But here's how I think about it. We have observations, we have a task, put it to VLM. VLM comes up with low-level tasks that we can pass to a low-level controller, and that low-level controller does the task and interacts with the world until it's completed, brings it back to VLM. What should I do next? So in this way, we are basically like separating these two components. What's the right level of interface between VLM and low-level controller? Is it language? It can be inherently ambiguous, and it requires that low-level controller to still understand the language. We don't want that. How about agent body positions? It's completely unambiguous, but it requires the VLM to understand the body of the robot. Again, not as scalable. So that's why simple command plus points in image plane is where we are going for. So let's say we put a point. It's very similar to the idea that RoboPoint also had, but go to the pink point, pick up that green point, place it on the blue point. So if we think of it that way, then now we can disentangle priorities. We can have a VLM that will basically tell me, I'll ask it, this is outputs of our model, point to where I should grab to flip the omelet. It points to the handle, and then I can have the low-level controller to do the short horizon real-world tasks. Okay, let's talk about data collection. So we had this in mind. We were designing Momo. We were getting good results. How can we make sure that down the line we don't have to reinvent the wheel? Let's just talk about data collection. Let's just collect data that later on we can use for this project. What do we need? We need point to text that describes these objects. We need to facilitate counting and some understanding of the environment. And we need to ground visual explanation in image by pointing. These models, these pre-trained models, already have a lot of this information. It's just a matter of how can we ground it? How can we show it that you were captioning this image as, oh, there is a laptop here. These are the features. These are the spatial information that you used to derive to this conclusion. That's why we just asked annotators to point and describe objects, collected also not present data, because that's also important. We don't want the models to always point to an object. And we had 2.3 million question pairs from 400,000 images. And with that, you see the Momo that we have today. We have some demos on our website. Go check it out and like play with it. It's pretty good, but that's not where we end. Training data and training script, training code will be released in a few weeks. And if you have any data, you want to fine-tune it, you can fine-tune it on only 8 GPUs. Do that. See what else can you get out of that. Is ChatGPT moment of robotics here? So the only thing that was left was the large range of tasks. And it seems like we can do that, right? So ChatGPT moment of robotics is here. Not yet. All of these, there's asterisks on each one of these items. I want you to see that. I want you to see that when I say large range of tasks, I'm still talking about pick and place. When I say generalized to truly unseen scenarios, I still mean unseen environments, but still, we haven't rigorously tried it. When I say easy adaptation to new domains, that's requiring skills that I've seen in pre-training. And when I say any embodiment, still results can be pushed. And I only showed you navigation results today. So going to manipulation is a whole other world. But I think we are getting closer, and we are taking it one step at a time. Let me tell you what I think is missing and what are the next steps that, if anyone wants to continue on these works, can take. Articulation and complex manipulation. We are designing a new simulation environment, which is MuJoCo based, because we are interested in doing more fine-grained manipulation. Speed. I know Sid has always been telling me, why are your videos sped up? And I agree with that. We need these inference times to be much faster so that the robots are not taking forever to do a simple task. That's another thing that we need to work on. The other one is error recovery. These modular approach that we have a VLM that is talking to a low-level policy, we are going to have errors that are cascading. We need to think about that. And the final is other modalities. I am bounding myself to RGB only because I'm using these pre-trained models because I want to pre-train that visual backbone on internet scale of data. How can we bring depth into this? How can we bring proprioception out to this? How can we bring point clouds to this? So these are all the questions that we can answer. And with that, we have 8 minutes for questions, it seems like. Good timing.
Questions? So one question is, a lot of things seem to work. What doesn't work? Like when you look at, like what is a surprising failure mode of the simulation models in the first 3 sections?
Failure, the first, I think I mentioned a lot of those. The manipulation is still limited to pick and place. Mm-hmm. So if I have a couple of objects here, and I want to pick up this MOG, right now there is a high chance that the arm of my robot is going to collide with this when it's trying to go for that.
Do we attribute those to like an RL problem, or is it a simulation problem, or is it a generalization problem?
I think it's more that we need to focus more on them as a question. Maybe it can be just some reward shaping. Maybe it can be just having some models that are better aware of collisions and occlusion. We don't really allow the models to do multi-object manipulation, so we don't allow. It's not really in our paradigm to have to like grab an object to empty out spots because we are focused on the longer horizon aspects of it.
Got it. Cool.
So you mentioned at the end that you guys are building a new simulator. Are like current ones like Isaac Sim not good enough for finding manipulation?
That's a really good question. We actually started looking into different simulations. So we believe in, if you want to do sim to real, we believe in scale, procedurally generated environments that we can build at scale, and we have all these assets that I didn't get to talk about. We can procedurally generate environments, we can populate it with this 1 million assets of objects that we have, that we also have like descriptions for it. We couldn't leverage those if we were to use something like Isaac Sim. So that's why we are more like focused on building it from scratch in MuJoCo, and being able to have these like scaled environments that we have this other project that you can get a natural language description of an environment, and we generate that house for you. And we wanted to use all of those scenes and all the works that we have built in that simulation environment. That's why we are building one from scratch.
So in the VLM part at the end, you talked about the interplay between how VLM kind of gives instructions to some low-level controller. And you said you're kind of goal conditioning it with like waypoints, and you're saying, hey, go to that pink spot. But how do you, like, what does this low-level controller look like, and how do you encode some sort of like uncertainty? So what if a cat runs in front of the robot, or like a human walks in front of it? How do you tell the low-level controller, hey, there's somebody there, you should stop? Or how do you navigate around that? How do you encode this uncertainty into the navigation? And how does the low-level controller understand that and stuff like that?
So we have never had added random occlusions in the middle of the episode. So our scenes have always been static. But because we have a lot of randomization, we realized that they're good at detecting these like occlusions that are coming, these collisions that are coming to the scene. So for example, a bunch of examples that I showed is like following a person or following a toy, and those are like dynamic, even though it has never, like, we are evaluating the model in dynamic environments, even though we have never trained on them. We don't really have anything during the training time to ensure that it's like actively learning during training time how to avoid dynamic obstacles. That can be done though, if you're interested in it. That's a project that can be done because it's basically like, it's very easy to add that component. One thing that I didn't mention, we already have a policy that gets a point and can navigate to or pick up an object that is pointed to. It was very interesting for me when I was testing it out in the real world. It was able to even, so I would give the point to, for example, a mug in the first frame, and I would start moving the mug around, and I would follow the object, which is interesting. I was not expecting it to work. I think it's just because of that pre-training, the frozen visual encoders that are strong, that the agent during training learns that concept of what is this object, what is this point, what does this point mean? It's pointing to this specific object. So that's why I need to follow that object. Anyway, I gave you a lot of details that you probably didn't ask for, but.
Other questions?
When there's no question, there's two ways that it's either the talk was really good, that everybody's so clear and they don't have any questions, or it was so bad that they're like, I don't know what to tell you at this point. So it's usually the second one, but I'm gonna.
One thought is you chose points as your interface, and OpenVLA chooses actions as its interface, and there's like a lot of stuff in between. Like, how do you think we should draw the line between VLM and low-level control? Do you have like, I guess you explored one choice, but how would you like go about investigating that spectrum?
So I'm all about simplicity. I always choose the simplest thing first, then add stuff that is needed to make it work. I think down the line will be something in between of like, the VLM will say a point and then some sort of an action, maybe even like in agent's coordinate frame, some points in that agent coordinate frame. But that's the first thing that I would try.
So for like this cross-embodied navigation century, or like, I guess, the evaluation and simulation, you use like this box to represent the robot, right? But this like only works for navigation robots because the robot's not like in the actual camera view, right? So how are you planning to like?
Actually, the robot is in the camera view. Okay, I'm going to tell you two things. First, the robot is in the view for many of the camera viewpoints. And what we are doing right now, which is not the ideal way, but it's just what we are doing, we have the segmentation mask of that body because it's simulation, and we are randomizing it with different shapes just to get that going. But we have the capabilities of randomizing the agent's body with any object from the Observer's asset. And that's the next thing that we're going to try. So basically, like having different body shapes and body meshes so that the agent, the policy learns that this is, oh, if I'm moving forward and this mesh that is in my view is moving with me, that's my body. But yeah.
Maybe like a similar follow-up question is that when you're training like the navigation thing with the box, do you randomize the size? Because across like the different robots that you like showed me, like they have different affordances. They can like go through like different paths. Like even the Unitree can go under a table versus like the Stretch might not be able to. So like, is there like a difference, or you're focusing on finding a policy that just like learns a single path that works for every robot?
No, it doesn't learn a single path for every robot because some of our robots are much bigger. That's actually, so I'm not sure if this is the question you asked or not, but one question might be, is it really learning anything about the body, or it's just learning to be like as conservative as possible? I don't know the answer to that. But that's a good question. I'll make sure we have that result in the paper.
All right, I think we're out of time. Let's thank Kiana again.